Welcome everyone. My name is Karelia La Marca and I am a master's in geophysics at the University of Oklahoma and a member of the ASPE research group. Today, I'm presenting my dissertation called Optimization of Deepwater Channel Seismic Reservoir Characterization using Seismic Attributes and Machine Learning. My committee members are Dr. Heather Bido, Dr. Matthew Prater, Dr. Sarah George, and Dr. Deepak Devegoda. These projects are a collaboration between the ASPE Research Group and the Chile Slow Systems Consortium at the Colorado State University. This is the outline that I'll cover today. I'll start with an introduction, talk about the dissertation structure, motivation and objectives, dataset and geological setting, some fundamentals, and then provide details with the chapter 1, 2, and 3 of my dissertation to finish up with conclusions, acknowledgements, and references. The dissertation is composed by three main chapters. I first will present the sensitivity analysis of seismic attribute parametrization to reduce misinterpretations, applications to deep water channel complexes. This chapter has been published in the journal Marine and Petroleum Geology from Elsevier, also has been presented at the APG and SCG conference in 2021 and published as a expanded abstract. It has been also awarded different prizes from Oklahoma State University, Houston Geological Society, and poster competition at OU. My second chapter is called Uncertainty Assessment in Unsupervised Machine Learning Methods for Deepwater Seismic Phases using outcrop-derived 3D models and synthetic seismic data. This chapter is currently under review in the SCG and APG journal Interpretation. It has also been presented at the 2022 Image Conference, has been presented at the Seismic Reflection Centennial Conference and the APG Mid-Continent Sectional. And I received 2 awards at the University of Oklahoma for presenting this chapter as poster. My third and final chapter is called Understanding Uncertainty in Deepwater Channel Seismic Phases Classification Applying Random Forest on outcrop constrained 3D models and synthetic seismic data. This one has been submitted to the SCG journal The Leading Edge. I'm pretty sure that most of you, if you like to travel, may be like me. That if you had the chance to pick a window seat, you will do it, right? Who wouldn't? Especially if you're a geologist. Like, look at these beauties you can see from that window seat. So basically, you can see, what is that? What we call channels, right? And look at all those shapes and how meandering they are. So guess what? In geology, we have a principle that is the present is the key to the past. And basically, everything that we see engraves a hint of what was deposited in the past and that now lies in the subsurface. But why am I mentioning this? Well, basically, this is what I would like to be an expert at in channels, and specifically those that are related to deep water settings. Channels are known for being one of the best reservoirs in different depositional settings, fluvial or deep water. And the channel architecture and phases will vary from system to system. So the interpretation of the channels are going to be cumbersome due to seismic quality or resolution. Look at this example of a dataset in New Zealand. So here we have a first square that will depict the minimum element that we can have in that seismic. So we call this a channel element, and it's comprised by different phases. So in this case, we have a channel axis in the center, then channel off axis in orange, margin in brown, and a slump or MTDs that will function as a barrier, usually at the bottom of that element. If we stack those channel elements, we will have what is called a channel complex. And we can find that here in this square, in this blue square. If we stack those channel complexes, we will find what we have, what we call a channel complex set, which is an amalgamated channel complex. And then why do I mention that interpretation of these channels may be cumbersome? So here we have a comparison of conventional versus high resolution data. And here we can see how with the higher resolution data set, where they were able to actually depict better those different sequences and architectures within the channel complexes. But how did it all started? So back in 2019, 2020, when I was doing my master's, I had the opportunity to look at those beautiful channels of pipeline 3D in New Zealand that some of you are familiar with. And I applied machine learning, a method that is called self-organizing maps, to come up with interpretations of different architectures associated with that channel. Something that we realize is that when well logs are not available, the interpretation will rely merely on the geoscientist and its experience. So in this case, we thought the mapping reservoir dimensions architecture are critical for exploration and production. And sometimes real data or outcrop base is not often available. And in this case, with the use of the data provided by Chile Slow System, consortium, we had the opportunity to test different seismic attributes, machine learning techniques, and see if actually those so-called black boxes were actually having an accurate prediction or an accurate clustering in the case of unsupervised. And we came up with three fundamental questions for the overall dissertation. Are we employing the right attributes and parameters to characterize channel architectures? Can we assess uncertainty in unsupervised machine learning methods for channel phases interpretation? And also understand the uncertainty in deepwater seismic phases classification using random forest. Therefore, the objectives of this dissertation are to test the sensitivity of seismic attributes in architectural element detection and to quantify uncertainty in seismic phases prediction using synthetic seismic data and machine learning. But I want to give you a little bit of geological context on the model that I used for this project. So this model was built upon an outcrop exposure located in the Ultima Esperanza district in the tip of Chile, South America. And the Magallanes Basin here is a retroarch four-line basin, and in the case of that was formed during the Indian orogeny in the late Cretaceous, and as a result, we have a beautiful exposure of around 4 kilometer thick deep water strata that was deposited in three major phases. So first we have thin bedded turbidites of the Punta Barrosa Formation, then a channel levee complex system that comprises the Cerro Formation, and the progradational slope system, Trespasos Formation, which is the objective of study, and subsequently a deltaic and fluvial Dorothea Formation. And this outcrop is located in Laguna Figueroa. So in this outcrop, a detailed bed to field scale 3D architecture outcrop based model was built, taking measure sections, GPS points, photo mosaic with using drones, and like a commercial package was used to actually come up with those models. And thank you to Dr. Stride and her team, it was able to actually represent those slope channels of the Trespasos Formation, assign realistic acoustic impedances, and perform 1D convolutions to come up with 5 forward seismic reflection models of 15, 30, 60, 90, and 180 hertz. In which case, you will see that for our second and third chapter, we will focus on the 60 hertz since it represents a more realistic seismic data set. And also take in account what we already mentioned, that we're going to be talking about 5 architectural phases, which are shale and levee, or that represent those thin bedded turbidites, channel axis in the center of the channel, then channel off axis, channel margin in brown, and slump and MTD. As a general workflow for the dissertation, we have that. We actually have this actual model that represents that outcrop and the distinct architectures. And we have the seismic data from with different frequency content. Then we have a seismic attribute analysis. Then we perform machine learning, both supervised and unsupervised, and I will explain what that is. And we will come up with seismic phases predictions that will allow to perform an analysis and quantify uncertainty by comparing with the actual outcome. Let's move on with the chapter 1. For each chapter, we posed a series of questions that we wanted to solve. So in this case, we wanted to perform a sensitivity analysis of the imaging of those architectural elements based on the frequency content, the seismic attribute choice, the analysis window size, and the effect of noise. Because I don't want to assume that you all are familiar with the concepts here presented, I want to define what a seismic phases is. In this case, it's a group of characteristics, reflection patterns that are unique from a body or unit in the substance. And what we do as geoscientists or geophysicists is to use seismic attributes to be able to interpret those seismic phases. And a seismic attribute is nothing but an algorithm applied to our seismic data, or what I call the tomography of the subsurface, and to be able to highlight those features and aid in the interpretation process. There are many seismic attributes that can be employed to interpret channels. Some of them will sharpen the edges, some others will highlight or give you hints on the composition of those channels. And there are thousands of seismic attributes that we could explore. And as interpreters, we are limited to display up to 3 seismic attributes at a time. So that makes us think about the necessity to actually use machine learning to make the most out of these attributes. But also, we need to know which parameters we're going to use. So the workflow we employed for this chapter was to perform exploratory data analysis and volume cropping. We perform a parameters assessment, assessing 3 main parameters: the frequency content, seismic attribute choice, analysis window, and addition of noise. And that will generate evaluating a 15, 30, 60, 90, and 180 hertz frequency content. Will give us the first case of effect of spectral bandwidth on the imaging of architectural elements. Then with the second parameter, which is the seismic attribute choice, we select amplitude accentuating, geometric, and instantaneous attributes to come up with the case 2, which is the attribute sensitivity to thickness and extent of stratigraphic elements. Then we have a third parameter, which is the analysis window. So we explore small, medium, and large analysis window to come up with the third case, which is the effect of analysis window size on the vertical smearing of stratigraphic architectures. And ultimately, we addition band-limited random noise of 5 and 30% to evaluate the effect of noise in the sensitivity analysis. This will allow us to come up with a workflow optimization that will allow the geoscientist to aid its interpretation and also document best practices in attribute parameterization to avoid pitfalls. For the sake of time, we are presenting just a couple of those results. In this case, we have a comparison between a 30 hertz that will be representing vintage seismic data and a say 60 hertz data set which will represent modern seismic data. So here we find that especially at lower frequencies or vintage data, that is what we usually have available. We have an underestimation of channel complexes and architectural elements, and actually the number of complexes, the size, shape, and the type of architectural bodies, like channel elements versus margins and elements versus complexes, were difficult to differentiate, regardless if we use an RMS seismic attribute, coherence attribute, or instantaneous frequency attribute. Actually, in the coherence attribute, we notice how the in the edge detection was proper or more appropriate as we increase the frequency content. And high RMS was found in those areas where we had the channel axis or stacked elements, similar to that instantaneous frequency. Another case we wanted to show is the comparison between the 60 hertz volume with 5% noise added and an increase in noise. So overall we see how the noise hinders the interpretation of those that channel architectures, especially when using coherence. After performing our sensitivity analysis, we came up with two pretty cool things. So first, we have built a table that will address the common pitfalls in seismic interpretation and how to avoid them, and also a workflow that a geoscientist can use just to like avoid pitfalls in interpretation. For instance, if you have your input seismic data, you ask like, does it have significant noise? If yes, you need to apply noise removal method. If it doesn't have noise, then what is the dominant frequency? You calculate resolution, you define an optimal window of analysis, and you then select the attributes according to your geological goal. In the case of channel element edges, we suggest the use of coherence. In the case of phases and channel fill, frequency, amplitude, or phase attributes, and then we make decisions based on if they are windows or not dependent, and then we co-render or apply unsupervised machine learning for interpretation. There are many analyses and insights we had from this chapter, but we're going to point out the main ones. So here in this chapter, we introduce the term stratigraphic mixing to define the vertical appearance or the smearing that occurs due to the inability to resolve a single channel element. We also noticed that higher bandwidth data, for example 90 hertz or 180 hertz, combined with a short analysis window, minimizes that stratigraphic mixing. And also that the attributes that are windows dependent, such as the root mean square, they show an improved imaging of the actual thickness of the channel when calculated using a small analysis window. In the case of edge detection attributes such as coherence, we noticed that reducing the analysis window doesn't necessarily provide a better imaging of those elements. So we suggest using an adaptive window with depth. And overall mapping of channel elements is hindered by adding noise to the data, and we suggest applying algorithms that will allow to eliminate or reduce that noise. Now we are presenting the chapter 2 that has to do with the uncertainty assessment in unsupervised machine learning methods. Similarly to what we had for chapter 1, we pose a series of questions that we will answer in the following slide. So this second chapter encompasses 3 phases. The data exploratory analysis, seismic attribute calculation, and input selection. A second phase that comprises the machine learning algorithms, and a phase 3 that will comprise the analysis. So first of all, we have a 3D geological model, and we have our amplitude volumes. We perform the attribute calculation of geometric, instantaneous, and spectral attributes. We use Python to concatenate them and come up with cross plots that will allow to select the best attributes, and perform then unsupervised machine learning methods using the ASPE software by using different clusters configuration. And then we perform a cluster analysis and geobody generation. We did a resampling and comparison with the original in a voxel by voxel base, and perform an uncertainty analysis that will estimate an error and provide a confusion matrix. But I'm talking about machine learning, and you may be wondering, what is machine learning? So machine learning is a subfield of artificial intelligence, which is defined as the capability of a machine to imitate intelligent human behavior. And overall, there are 2 classical machine learning techniques. Supervised, that basically is when we know the input and the output that we want to classify, and unsupervised methods that basically we know the input, but we don't know exactly what are going to be the results or the clusters form. So in this case, we're going to focus in the case of supervised methods in classification and unsupervised methods in clustering. But now, how do we know that we should use machine learning? So people are using machine learning pretty much for everything that they can think of. And as a good professor taught me over my career, if you can actually apply regression or a simple method, it will be better than applying machine learning technique just for the sake of like science. So in this case, the reason why we're using machine learning is because we have, let's imagine a synthetic seismic volume of 60 hertz, and the volume has about 30 million voxels. And if we computed seismic attributes, let's imagine that we're using 5 volumes, that will be 150 million voxels. So we're talking about big data. And in this case, the machine is able to handle all of that information. So extract patterns from more than 3 seismic attributes at a time, which I already mentioned is the limitation we have as interpreters. And also, it has been noticed that because we're working with multidimensional projects or problems, the machine is able to find relations and patterns that humans wouldn't normally do. Then, for the seismic attribute selection, there are at least 3 different strategies for attribute selection in unsupervised methods. So we can actually pick correlate candidate attributes to determine which are statistically dependent. We can use a dimensionality reduction technique such as PCA or ICA. We can also use the interpreter's geological experience and understanding attributes. In this case, we use a combination of the first one and the last one to come up with these attributes that you see here: instantaneous envelope, RMS amplitude, peak magnitude, and spectrum magnitudes of 20, 40, and 55 hertz. We already showed how self-organizing maps was used by by us in 2020 to come up with like deepwater seismic phases. But also GTM is another powerful technique that has been used successfully in various fields to model complex high-dimensional data. So, for instance, Ryan Verma used it for channel phases interpretation. It has been used for reservoir productivity and also for deep water seismic phases. And GTM comes to solve the self-organizing maps drawback that is adding now convergence and allows to select a learning rate. But how do those self-organizing maps and generative topographic maps work? So we're going to start talking about an initial set of data points that are inputted in lower dimensional latent space. And then in both cases, the data is projected onto a higher dimensional space. In the case of self-organizing maps, the best matching units are selected via weighting, assigning weights, and they represent the cluster. So in this case, the data points are going to get at the end closer to each one of these, and that best match unit is going to represent that cluster. In the case of GTM, a series of basis function centers are projected, and Gaussian probabilistic density functions occur around each vector, and then the manifold plane adjusts. So here we can see a pretty cool animation on time slices on how those channels are actually visible when we perform GTM. And these methods show that interpretation on architectures can be done using more than 3 attributes at once and show the channels, right? But what those color mean? So here basically what we have by using a combination of 3 clusters that is given by the elbow plot, We have one of the clusters that is representing channels, so we basically generated geobodies out of that. Then we have a green cluster that will represent the mass transport deposits, and then we have the background shale, which is the thin bed of turbidites, representing another cluster. So in this case, the green orange cluster will have an error of 8%. So overall, what we can say is not every cluster can be related to specific phases, and some architectural elements can be missed due to the nature and resolution of the data. So this is how we actually studied. But then we thought, like, what if we actually use commercial software and use the default parameters and go through the process like if we were just a regular interpreter and evaluate the performance of the different cluster configuration comparing self-organizing maps and GTM. So in this case, we compared a configuration of 36, 81, and 256 clusters, and what we did is manually interpret those phases and assign clusters that would potentially represent each one of those phases. And overall, what we see is that the 81 clusters seem to show smoother phases, and that the GTM seems to better represent actual phases than the sum. And then we decided to perform the quantitative assessment. So we needed to do the geobody definition. Therefore, we came up with some equations that will allow to basically distinguish all those different architectural phases. And that way, we could generate data frames that we could input in Python and discriminate those different or perform the uncertainty quantification. So that way we are comparing a truth model versus the unsupervised machine learning model. We are using common clustering arrangements, so user thinking, and determining errors and calculate correlation matrices. Then we were curious about in which ways we could evaluate the performance of those machine learning methods. So although it's an unsupervised machine learning technique, we thought that we could use metrics like precision, recall, and F1 score, and also correlation matrices to evaluate the performance of those elements. Because actually we have the actual response, which is pretty unique. But in this case, I'm highlighting the F1 score and the weighted average because it's the one that we focus on, since we have an imbalanced data, which means that we have more proportion of shales than other types of phases. When we evaluated the results on the error estimates for uncertainty quantification, we found out that models have overall high accuracy, and the self-organizing maps of 36 clusters has the highest weighted average with 94%, followed by GTM 81 with 93%. So just one of the classes, phases 0 or shale, in each model has the higher precision and recall, as you can see here. So that talks about lower error in predicting that phases and cuts our attention. Also, models don't show good performance for the other evaluated phases, being channel or phases 2, that is channel of axis, and channel 1 axis, the near best in performance, followed by MTD, and then margin, so being margin the worst phases predicted. So here I wanted to show actually the impact that that misclassification has in volumetrics and overall, like, in interpretation. So here we have the actual model, how it should look like, okay? And we have one of the best results, the GTM 36 results. So here we see how in a voxel by voxel comparison, we have a correct phases of our prospective phases, And however, we have incorrect phases of channel margin where we're supposed to have, or shale where we're supposed to have mass transport deposits. So this has implications not only in economic for a company, because you could be underestimated or overestimating volumes, uh, so losing money, or also in safety, because if you get to interpret or misinterpret an MTD, and that is acting as a baffle or barrier, and it could be unsafe and cost a lot of money. Now, to highlight the main takeaways of this chapter, we say that we introduce a new approach to assess uncertainty and unsupervised machine learning methods. This is something that hasn't been done before, because people not often have a ground truth data set like the one we had. So that gave us, an idea to actually come up with this uncertainty assessment. We also found out that the reduction of clusters don't necessarily offer an output that is easier to interpret, or using more clusters actually provide the best accuracy. So you need to put a lot of thinking of how many phases you may be finding, and give it a little bit of room. And also you could use even an elbow plot to come up with a statistically proper cluster amount. And overall, we noticed that, as expected, the GTM has a slight better performance overall as compared to the self-organizing method. However, there's not a single cluster or set of clusters representing each phases, and this is related to the fact that the resolution is going to be different. In each, it's related to the resolution in the seismic, and both methods reflect the quality of the input, don't have controls for imbalanced data. So even though our inputs are good, the fact that we have more proportions of shale will affect the classification, or the prediction of those clusters. We also recommend the use of supervised methods over unsupervised whenever possible. Now we will present chapter 3, which aims to understand the uncertainty in deepwater channel seismic phases classification, but applying a supervised method called random forest. And these were the questions that we posed for this chapter. So this is the workflow that we created to address uncertainty in supervised methods using our dataset. So we have the synthetic seismic dataset of 60 hertz, and then we have a ground truth 3D phases model, which we have divided in an upper section and a lower section. So the upper section allowed us to define the phases or labels and to train the model, and the lower section was set aside like an unseen data set that we will use as a validation, and we will explain that we don't actually normally need that in random forest, but we're doing it just to test our model. So follow me. By having that upper part of the model, we define the phases, labels, and we define the training data set by merging these with the computed seismic attributes of or features. And once we have our training data set, then we perform a max scalar transformation, and we perform the random forest and hyperparameter optimization in a series of 6 tests that we will show, and select the best parameters and apply the model, then assign the variable importance, confusion matrix, and export the CY volumes, and then perform a visual and numerical analysis of that. And then with the validation dataset, basically we apply the model and compare it and see how the performance was. And now we have another method, random forest, which in this case is supervised machine learning, and it was introduced by Leo Breiman in 1996. And it is, as its name refers to, a set of decision trees okay, ensemble of decision trees, with the final result being determined by the majority within the individual results. And random forest can be used as a regression or classification technique. So regression is if you have continuous data, like what looks. And classification technique is the one that we're using since we want to come up with single faces. And we use it because they can handle multi-class classification. They are proven to be very sturdy machine learning techniques that we are currently using in the research group by Mario and Marcus. For instance, they show that really good results, promising results. It is relatively fast to train and predict, and it provides a measure of the variable importance. Also, you have we want to clarify what a features is. So in this case, we're using features as seismic attributes. The labels are going to be phases, and in this case, we have a training data that then is tested, and we have the overall random forest. And if you find something that is called validation, in our case, it would refer to the use of a new unseen data set, but it doesn't mean that random forest requires a validation. So we perform a sensitivity analysis on hyperparameters optimization using a grid search. But in this case, we call it hybrid grid search because we perform 5 tests or 6 tests. Each one of them will test a different parameter so we could understand what was the tendency. So for instance, when we evaluated the minimum sample split, we noticed that the smaller the better. Then maximum number of samples, basically the larger the better. Maximum depth, we should reduce or keep. Number of estimator, the larger the better. And that way we came up with a final test and hybrid grid search that will help us optimize those hyperparameters. So here we're gonna show the correlation or confusion matrices from the original or test one versus the optimized random forest. And here we can see how there is an accuracy increase of 15% with the use of optimized parameters. Also, if we didn't optimize hyperparameters, we will be overestimating the channel axis faces and underestimating thinner faces such as the channel margin and MTD. Then do you remember that validation test or that validation data set that we set aside? So basically, when we apply the optimized random forest model to that one, we obtain a decrease in around 30% accuracy when the model is applied to unseen data. And the channel, although the channel complex's location and orientation were well predicted, the channel axis, shale, and MTD faces show predominance over the other channel faces. So that's something that to take in account because it's not a one size fits all problem. The good thing about this is like when we inspected it visually, we saw that although there is a higher misclassification, we have a correct position and overall faces distribution, which is very useful in exploration when sometimes we don't have much data. So if we could somehow come up with a model like this that could be applicable to analog data sets or geological settings, at least we would know that it will perform relatively well in finding the disposition of the channels of the main architecture. So as final remarks is that there are misclassifications that are occurring mostly for channel faces being classified as shale. So we attribute these misclassifications to possibly be overfitting, which means that the training accuracy is high and the validation error is low. Um, then we could also have limited resolution of the seismic data that results in stratigraphic mixing, where thinner faces are overpowered by nearby thicker faces. We also have the presence of imbalanced data. So we have shale more than other phases, although random forest is supposed to like come up or uh, yeah, work well with this. And then random forest doesn't work well with sparse data. So in cases where the margin phases were located more isolated, it was hard to classify those. Also, we need more hyperparameter tuning or the use of alternate features. We also have that random forest offer high accuracy but is sensitive to input variables, labels, parameterization, and proportions of data. The use of hyperparameter optimizers such as the grid search allows for an increase in the classification accuracy. And although there are misclassifications, the random forest showed to be a powerful tool to interpret correct position and overall deep water channel phases configuration, which reduces uncertainty, especially in non-calibrated basins. To sum up our final conclusions for the dissertation is basically we want to point out the use of synthetic seismic data and outcrop-derived models to actually test perform sensitivity analysis, understand what the attributes were depicting, how the different frequencies were behaving, to actually come up with a new approach to assess uncertainty in machine learning and unsupervised methods, which are not often understood and are very could be very biased by the human interpreter. Also, we come up with the evaluation of a robust algorithm, which is random forest, and oftentimes we have a single, well-logged data, a single point, but we don't have a whole model that will actually tell you how accurate these models are actually going to be. And if we get to apply that to unseen data, if they're going to be able to actually come up with something that is meaningful, which indeed we demonstrate that it was the case. So, addressing uncertainty in machine learning methods is necessary to properly select algorithms that provide, a better reservoir model, because this has a direct impact in volume estimation, flow simulation, and those are critical not only for oil and gas industry, but also in new energy studies like CCUS and geothermal resources development. So yeah, we cannot fully eliminate uncertainty, only assess.